So now it is visible?
Yes,
Yes, it is.
Okay. Thank you very much.
You can
Okay.
see.
Okay. Hello all. Today I will be going to, first of all, I would like to thank organizers for giving me opportunity to speak my current work. So the title of my presentation is Pressure Induced Anomalies in Phonon Frequencies and Structure of Low Temperature Phase of Copper Cyanide. This work is carried by me under the supervision of Dr. Rekha Rao and Alka Garg. So this is outline of my presentation. I will just briefly give motivation and then show experimental details and then discuss some of the results and then I will summarize. So motivation. So the materials which are reported to show where external stimuli such as temperature or pressure, when they induces some anomalous responses, are considered to be exotic. For example, the materials which are NTE, means negative thermal expansion material, or negative linear compressibility materials, they are considered exotic. NTE means the material contracts upon heating, and NLC means material expand along a specific direction under hydrostatic pressure. So for such materials may have key application in the development of some kind of composite materials where they can have like some effective zero compressible, zero expansion material with temperature, or incompressible materials with pressure. Also, there are some kind of things have been explored to develop some kind of artificial muscles or amplification of piezoelectric responses for next generation sensors and actuators also have been explored. So based on this negative linear compressibility materials. In literature, it is also speculated that strong negative linear compressibility can be found in framework structures that also show anisotropic NTE, although both NLC and NTE can have a different, like they can be independent phenomena, but if it has been speculated that where anisotropic NTE is there, their NLC is also stronger. There are some limited reports available for NLC. Among them, the cyanides, the silver, these cyanides show both the behaviors together, NLC and NTE. And cyanides are also have been reported to show pressure-induced structural phase transitions, amorphization, and decomposition. For example, this silver cobalt cyanide, it is actually reported to show colossal anisotropic thermal expansion behavior. This shows pressure-induced structural phase transition at a moderate pressure of 0.2 GPa, followed by a pressure-induced amorphization above 13 GPa. The same compound is also showing pressure-induced decomposition when the pressure is released. Interestingly, this sample shows very large negative linear compressibility value, which is very large for this sample. But because this sample changes the structure at 0.2, so that negative linear compressibility range is quite low for this sample. So thus further many other samples have been explored for getting this NLC behavior for a longer pressure range. So this potassium and manganese silver cyanide have shown a pressure transition at 2.8 GPa with NLC at it is not like as better as this, but this is also quite a better value. But the pressure range is actually increased from this. Also, similarly, this potassium cadmium also have shown NLC behavior, and zinc gold is also shown. But among these reported structures, they all show NLC behavior, but the pressure ranges are quite low. Up to this, they are showing NLC behavior. So, and the basic. Hello, am I audible now?
Yes.
Okay. So among all these cyanides, the NLC behavior is because of hinging of their framework structures. All are the structures are frameworks in these cyanides. So, and then in the literature, we found that this metal cyanide MCN, where M is gold, silver, or copper, they are linear chain structures. When M is gold or silver or copper, they are showing tetragonal structure. And copper has two structures. One is with this tetragonal and one is orthorhombic. When it is in tetragonal structure, so these tetragonal structures are actually negative thermal expansion in C direction. And while this other structure of copper, which is that nomenclature is the tetragonal structure of copper is high temperature phase, and this orthorhombic phase is the low temperature phase, which is also NTE in this direction. It is in A direction. So in the literature, there exists only single report on from experimental point of view for the high pressure studies of this low temperature phase of copper cyanide have been explored up to 4 GPa using Raman spectroscopy, where a few soft modes were detected. So present motivation for our this study is we are going to study the high pressure structural behavior of this low temperature phase of copper cyanide using Raman and X-ray diffraction studies. So experimental details, we have used this micro Raman LabRam HR evolution instrument, which is at our lab at SSPD. And we have used ultra low fluorescence filter, which can record Raman spectra from 10 centimeter onwards using 1800 lines per mm grating. And for high pressure experiment, X-ray diffraction experiment, we have used Electra express beamline of Electra synchrotron source, which has been financially supported by DST. So for high pressure experiment, we have used this mobile type DAC, where we have used pressure transmitting medium 16:3:1 methanol ethanol water mixture, which is actually hydrostatic up to 10 GPa. And for pressure calibration in Raman experiment, we have used Ruby fluorescence method, and in X-ray, we have used copper equation of state. For results and discussion, so that low temperature phase copper cyanide is orthorhombic with C22221 space group. This is actually a wave-like 1D chains of two coordinated copper atoms, which are bricked by side disordered copper cyanide. So these are the unit cell of this copper cyanide orthorhombic structure. I have just shown it in these different directions. So the polycrystalline sample which we have used is actually purchased from Sigma Eldridge, and the X-ray also confirmed this the single phase of orthorhombic phase. This is the Raman spectra what we have recorded from our instrument. So this Raman spectra matches with the previous report, but additionally we have got two extra peaks using our low fluorescence filter, which at 20 and 30 centimeter inverse, and this mode I have been assigned using that report. So for high pressure experiment, this is the Raman spectra of this orthorhombic phase LT-CuCN at different pressures. We can see these two peaks are moving in the forward direction. They are showing the hardening behavior, but the mode which are written here, the 6 modes, this is a CN stretching region. It is clearly showing some anomalous shift that this peak is moving in the this Raman mode frequency is decreasing. That means they are showing some softening behavior. And above 7 GPa, the Raman spectra also completely disappeared. So probably there is some kind of structural phase transition or maybe electronic phase transition happening above 7 GPa. And these soft modes are also maybe leading towards some kind of phase transition. So this is also this is a figure variation of Raman mode frequencies of LT-CuCN with pressure. We have also listed the mode gradation parameter calculated using bulk modulus. Bulk modulus we have also found out from the X-ray diffraction experiment, which I will be anyway discussing in the next slides. So from here, these gradation parameters for these 6 soft modes are giving negative value. And in the expression of alpha, the thermal expansion coefficient, this mode gradation parameter is coming here. So probably this these soft modes are also contributing to the negative thermal expansion behavior of this compound. But these two compounds, these two modes, which are very low frequency modes, they are giving positive value. So they might not be contributing in this alpha. So for X-ray diffraction experiment, this is the X-ray diffraction data for CuCN at different pressures. So we have used copper. So this is the copper for pressure marker, and this is a gasket peak. So the main reflection peak at 7.7 this 7.7 degree is showing positive behavior. But interestingly, the anomalous shift of this particular peak is seen here, which is moving left side. That is also actually, it is a 201 plane. That means the interplanar spacing between 201 is actually getting increased under high pressure. And In the preliminary observation, the structure looks stable up to 20 GPa, but the main reflection disappears above, like it gets disappeared. That needs to be investigated. But interestingly, this the main interest for this study is this particular peak is getting in like anomalous shift. So probably it is indicating some kind of negative compression behavior. So we have fitted the X-ray pattern up to 7.9 GPa with this ambient structure. It was fitted nicely. And this is the two ritual refinement data which we have fitted up to 7.9 GPa. This kind of fitting has been there. And then we have plotted the variation of lattice parameters using pressure. We can see the this C parameter and B parameters are decreasing, which is a normal behavior. But interestingly, the A lattice parameter is increasing. Here we have plotted the relative lattice parameter. Here also we can see A parameter is increasing. So we have fitted the this variation with second order Birch-Mirgon equation of state, and we have found out the compressibilities. But this was not fitted with the Birch-Mirgon equation. So we have fitted this with polynomial, cubic polynomial, and found out the linear compressibility along A direction.
Mr. Kesari, can you quickly wind up?
Okay, yeah, just so we have compared this linear compressibility with the reported. But in our this studies, we got this NLC behavior in a longer pressure range up to around 6-7 GPa in comparison to this without any pressure transition. Okay, so this bulk modulus is also have been calculated here. So in summary, this structural vibrational investigation of orthorhombic have been investigated, and we have got NLC along A direction and for a longer pressure range without any phase transition within that range. So and the two soft modes were also 6 soft modes were also being investigated. Okay, thank you.
Thank you, Mr. Kesari.
Yes.
I have a quick question.
Yes.
Could you please go to your slide at 20 up to 20.2 GPa Raman slide?
Okay. Yeah. Raman actually was done up to
20.2 GPa. Now you study there is no structural transition up to 20 GPa.
No, it is X-ray diffraction pattern. Yeah.
That one. Oh, sorry.
Yeah.
So you told there is no structural phase transformation. So
yeah.
So you see if you look at this peak at around 2 theta 8.
Yeah.
So this peak is at around 15.7 GPa. At 18.2 GPa, this peak is completely disappearing, right?
Yes.
And then you can see a lot of sharp changes in the intensities as well. So there is definitely a structural phase transition.
Yes, sir. Actually, this is our preliminary result, and like there are certain peaks which looks like there is a appearance of new peak, and it is also getting increased. But symmetry-wise, this peak was also allowed. So we are actually investigating.
Your peak is disappearing. Your peak is See, this strong peak is disappearing, and the first peak you see with pressure, its intensity is getting down. So overall, there is an intensity distribution and also disappearance of peaks. So it should be a structural phase transition.
Yes. Even our Raman spectra above 7 above 8 GPa is also not there. So probably both are. So, but the work is still under investigation. But the main point of this study was we are getting some anomalous shift of this peak. Yeah.
You mentioned that Birch-Mirgon equation could not be applied something, right? I'm not very clear about it. But one of the
I was showing that the variation of C parameter, the A parameter was increasing with pressure, which is actually anomalous behavior with.
You use the Zen's law. Zen's law, because you are talking about the lattice parameter, right?
Yeah.
So use the Weber's law can be used. So when you talk of volume contraction, should be there, right?
Yes. Volume is compressing. Yeah.
The Zen's law, right? If you are going to HCP solid or some kind of thing, the Weber's law, Zen's law should be used, and the Birch-Mirgon should be applicable here.
Yes. In volume versus pressure, I could fit it with Birch-Mirgon equation and bulk modulus have been explained.
Mirgon equation is not to be. That's not a right case. Okay.
Yes. For a linear, we have fitted with that polynomial. Yeah.
Okay. Thank you very much, Mr. Swayam, for a nice presentation. We'll move on to the next presentation.
Analytical numerical approach. Congratulations. We are pleased to present you a very humble memento, which is a hand-carved small elephant, and a certificate will be mailed to the award winners. You can show. Is it visible now? Okay. So the other award goes to Mr. Swayam Kesari from Bharg BRC, Bombay, India, for his oral presentation on pressure-induced anomalies in phonon frequencies and structure of low temperature phase of copper CN. Congratulations to all the team. The other best oral presentation award goes to Mrs. Rajita R. from ICReAcH Kalpakam, India. The presentation is for her work on pressure-dependent phase transformations in heat-resistant explosive, BDNAPM. Congratulations to Mrs. Rajita. The next one. The other award goes to Ms. Anurupa Behata from IIT Hyderabad, India, for the presentation on quantum topological transition observed in layered ferromagnets, lithium manganese fluoride using first principle study. And Mrs. Gayatri V from ICReAcH Kalpakam backs the other oral presentation award for high pressure studies on pristine and lead substituted bismuth based high temperature superconductor.